Hi, today we are going to discuss surface integrals. So, how can we evaluate them? We will see with more detail surface integration over a scalar function. Concept-wise, surface integrals are really similar to double integrals. With double integrals, we would integrate in respect to a region R, which is bidimensional. We can sketch the situation, so we would have here our region R, as well as the surface described by the function f. Double integrals allow us exactly to assess the volume between those two surfaces. So for that, we would need the area of the region R, which we can assess, as well as the distance between the two surfaces, which we also can assess. So we can evaluate the double integral. The train of thought for surface integrals is exactly the same. However, S is no longer a two-dimensional region, but a three-dimensional region instead. This poses some problems because to evaluate the volume between the surfaces green and blue, we would need to be able to evaluate the area of a non-flat region. The solution is to transform S into a two-dimensional region, R, and then it would be just to evaluate the double integral as we would before. For that, we need to parameterize the surface S, which can be described using two independent variables, for instance, u and v. Let R be the parameterization we work with, which gives us for each couple of u and v a point in the surface S. We need to assess the partial derivative of R in respect to u, as well as in respect to v. After that, we can finally transform the surface integral into a double integral, and then it's just to calculate it. In a special case where S is given by Z as a function of x and y, we can parameterize it as x equals x, y equals y, and z as a function of x and y. Once again, we evaluate the partial derivative of r in respect to x and y, as well as its cross product, which will be given by the square root of the sum of the partial derivative of z in respect to x power 2 plus the partial derivative of z in respect to y power 2 plus 1. This means that we can rewrite the main expression for this case as such. Let's see an exercise. Here you are asked to evaluate the surface integral over the function y, where s is defined as z equals 2x plus 2y, where x is bound between 0 and 1, and y is bound between 0 and 2. Firstly, we need to take care of the parameterization. So in this case, we would have x equals x, y equals y, and z as a function of x and y. And as we saw previously in the theoretical explanation, that allows us to use this expression. So now we just need to assess the partial derivative of z in respect to x and in respect to y. And using the expression from the previous page, we can evaluate the surface integral as a double integral from 0 until 1 for x and 0 until 2 for y over the function y times square root of 6 dy dx, and then it's just to solve the double integral. It's nothing special, really simple, and then at the end you should get 2 times square root of 6.